Okay. Okay, good night world. My name is ATM4131 and welcome to my stream. Yeah, so this nice Atmachine learning session is just, well, basically me reading a book, textbook. And yeah, copyright check. Copyright check. I wanna try if this got taken down or not. Because this is, well, I don't really know the copyright about textbooks on stream. So yeah, I'll probably just stream it and let's see what happened. Okay, then bacane sing kalem ya Pak. Oh. Oh, halo Leonardo Ganal P. Halo Babe. Hello Zikri, welcome to my stream. Halo juga Papa di stream. Welcome to my stream. So, yeah, probably for tonight I will just read the first capture of this. Oh, yeah, capture one. Wait. Where's mana tadi? Where's the first capture? Mana sih? Males scroll. Oh, the first capture is not too long. For me at least. Okay. Mana scroll. Where? Oh. Oke, kalau takut kena copyright jangan ditampilin. Well, request bacain paper Greg Cashman Introduction to International Relations. Well, about the copyright, I'm not. Well, I am more like, let's see what happens. Is this gonna be taken down, or am I gonna get an email about this? But okay, basically I'm just testing the waves. Let's see what happens. And for requests, for now I don't take any requests, but probably in the future I will take requests on Twitter perhaps. But yeah, for now let's just read the introduction to quantum mechanics with me. Okay, let's go. The capture 1, the wave function. 1.1, the Schrödinger equation. Imagine a particle of mass m constrained to move along the x-axis subject to some specified force F xt, figure 1.1. How do I pronounce the functions though? So, okay, ini kayak dongeng sebelum tidur tapi bukunya berat. Well, if you wanna sleep to this stream, well, it's up to you. Okay. It's okay. I'm not gonna met or anything. You wanna use this for sleep? Well, feel free to sleep to this stream, anyways. Okay, then where am I again? Oh, okay. The program of classical mechanics is to determine the position of the particle at any given time, xt. Once we know that, we can figure out the velocity. The phi equals to differential. I can't read mathematical notations, so let's just skip the notation part. Okay, the reason I choose to display the book anyway is because there's like a ton of mathematical equations that I don't really know how to pronounce it. Just like, yeah, the phi equals to the differential x to t or something. I don't know how to pronounce that, so let me just show you the the whole book to get the idea. Okay, once we know that, we can figure out the velocity, the momentum, the kinetic energy, or any other dynamical variable of interest. And how do we go about determining x, t? We apply Newton's second law. F equals to mass times acceleration. for conservative systems, the only kind we shall consider, and fortunately, the only kind that occur at the microscopic level. The force can be expressed as the derivative of a potential energy function F equals to minus dou V per dou x. And Newton's law reads m, how do I pronounce it? It's m d square x per d t squared equals to minus dou V per dou x. These, together with appropriate initial conditions, typically the positions and velocity at t equals 0, determines xt. Quantum mechanics approach this same problem quite differently. In this case, what we are looking for is the wave function. How do I pronounce this Greek letter? It's V. Is it V or psi? Wait, how to pronounce that? Well, it's not V. It is psi. It is psi. Yeah, psi xt of the particle, and we got it by solving the Schrödinger equations, just as shown. I'm not gonna say that. Oh, the notes. Magnetic forces are an exception, but let's not worry about them just yet. By the way, we shall assume throughout this book that the motion is non-relativistic. Oh, sekali menyelam 2-3 pulau terlampaui. Yeah. Where am I again? Oh, this is the illustration, figure 1.1. A particle constrained to move in one dimension under the influence of a specified force. Here, I is the square root of -1 and h is Planck's constant. H with the funky stripe. Probably I will say it the h with the funky stripe. Yeah, is the Planck's constant, or rather his original constant divided by 2 pi. Planck constant equals to h per 2 pi equals to 1.054573 times 10 to the power of minus 34 joule second. The Schrödinger equation plays a role logically analogous to Newton's second law. Given suitable initial conditions, typically psi x0, x0, the Schrödinger equation determines psi xt for all future time, just as in classical mechanics, Newton's law determines xt for all future time. Okay. And now the 1.2, the statistical interpretation. Wait. The stream doesn't show the full page. Like there's something that is kind of blocked. So probably I will just resize the original. I will resize the original first. The original. Oh, this. Probably this is okay. Okay, 1.2. The statistical interpretation. But what exactly is the wave function, and what does it do for you once you got it? Yeah. And what does it do for you once you've got it? After all, a particle by its nature is localized at a point, whereas the wave function, as its name suggests, is spread out in space. It's a function of x for any given time t. How can such an object be said to describe the state of a particle? The answer is provided by Born's statistical interpretation of the wave function, which says that how do I pronounce this? Cxt absolute square gives the probability of finding the particle at point x at time t or more precisely, just as written. So the wave function is just the probability of finding the particle between x and the x plus dx at time t. So it is just a probability of finding a particle there. It's different than the classical mechanics where, yeah, assume there's an object placed at one place and it will always stays there. The probability is 1 because it's there. Yeah, basically it's there. It's just finding there. So the probability of finding the object there is just 1 or 0. It's either 1 or 0. It's either nothing or not at all. It's either there or not there. But in the quantum realm, from the wave function, we find that the the particle is just the probabilistic. Due to the probabilistic nature, it just determines the probability of finding the particle between x and x plus dx. So for the wave function in figure 1.2, you'll be quite likely to find a particle in the vicinity of point A. Wait. 1.2? What? What do you mean? Oh, 1.2 is in the next page. Okay, let's just read it first. You will be quite likely to find a particle in the vicinity of point A and relatively unlikely to find it near point B. The statistical interpretation introduces a kind of indeterminacy into quantum mechanics. For even if you know everything the theory has to tell you about the particle, to its wave function, you cannot predict with certainty the outcome of a simple experiment to measure its position. All quantum mechanics has to offer is statistical information about the possible results. So just as the illustration said, this is this wave function peak at A and it's nearly non-existent in B. Just like this, it's nearly touching the x-axis in the picture. It means it is almost 0. And look at A, it got a tall peak, the tallest peak in the graph. So you will be more likely to find a particle in the point A rather than B. Okay. This indeterminacy has been profoundly disturbing to physicists and philosophers alike. Is it a peculiarity of a nature, a deficiency in theory, a fault in the measuring apparatus, or what? Suppose I do measure the position of the particle and I find it to be at the point C. Question: where was the particle just before I made the measurement? There are 3 plausible answers to this question, and they serve to characterize the main schools of thought regarding quantum indeterminacy. Oh, that's the 3 position. Okay. That's the 3 position about the quantum indeterminacy, about the quantum mechanics. The first one is the realist position. The particle was at C. This certainly seems like a sensible response, and it is the one Einstein advocated. Note, however, that if this is true, then quantum mechanics is an incomplete theory, since the particle really was at C, and yet quantum mechanics was unable to tell us so. To the realist, indeterminacy is not a fact of nature, but a reflection of our ignorance. As how do I pronounce this? The Spaniard put it, the position of the particle was never indeterminate, but was merely unknown to the experimenter. Evidently, C is not the whole story. Some additional information known as a hidden variable is needed to provide a complete description of the particle. So basically the realist is just is there. It is the what they call it, the particles, the atoms, just like ordinary things. Yeah, the particle was at C. Yeah, it was at there. It is there. It is here, like that. And the second one is the orthodox position. The particle wasn't really anywhere. It was the act of measurement that forced the particle to take a stand. So how and why it decided to on the point C, we dare not to ask. Oh, we dare not ask. Oh my god, I swear the author of this book, and Jordan said it start me. Oh, hello Afi. Is this the correct smart sleep hypnosis ASMR channel? Well, I'm just reading the quantum mechanics book. But if you decided to sleep on this, well, it's up to you. Feel free to sleep on the stream. Okay. Jordan said it was starkly observations not only disturb what is to be measured, they produce it. We compel to assume a definite position. This view, the so-called Copenhagen Interpretation, is associated with Bohr and his followers. Among physicists, it has always been the most widely accepted position. Note, however, that if it is correct, there is something very peculiar about the act of measurement, something that over half a century of debate has done precious little to illuminate. Am I gonna wake up smarter? Well, I don't know. I don't know. You may wake up smarter, you may wake up dumber, or you may wake up just like before you sleep. Okay, and then the third position, the agnostic position, is refuse to answer. This is not quite as serious as it sounds. After all, what sense can there be in making assertions? How do I pronounce this assertion? The assertions about the status of a particle before a measurement. When the only way of knowing whether you were right is precisely to conduct a measurement, in which case what you get is no longer before the measurement. It is metaphysics in the pejorative sense of the word. To worry about something that cannot by its nature be tested. Pauli said, one should know more like one's brain about the problem of whether something one cannot know or anything about exists all the same. Then about the ancient question of how many angels are able to sit on the point of a needle. For decades, this was the fallback position of most physicists. They tried to sell you answer 2, but if you were persistent, they switch to 3 and terminate conversation. Oh my god, I swear Mr. Griffiths made the the best disclaimers on the on the book. I swear. Until very recently, all three positions, realist, orthodox, and agnostic, had their partisans. But in 1964, John Bell astonished the physics community by showing that it makes an observable difference if the particle had a precise to unknown position prior to the measurement. Bell's discovery effectively eliminated agnosticism as a viable option and made it an experimental question whether 1 or 2 is the correct position to appreciate Bell's theorem. For now, suffice it to say that the experiments have confirmed decisively the orthodox interpretation. A particle simply does not have a precise position prior to measurement any more than the ripples on a pond do. It is the measurement process that insists on one particular number and thereby, in a sense, creates the specific result, limited only by the statistical weighting imposed by wave function. Wait, I'm gonna respond it. But what if I made a second measurement immediately after the first? Would I get C again, or does the act of measurement count up some completely new number each time? On this question, every time is in agreement. Oh no. Oh no, I'm overheating. On this question, everyone is in agreement. A repeated measurement on the same particle must return the same value. Indeed, it will be tough to prove that the particle was really found at C in the first instance. If this could not be protected, wait, where am I? Where am I? Where am I? How does the orthodox interpretation account for the fact that the second measurement is bound to give the value C? Evidently, the first measurement radically alters the wave function, so that it is now sharply about C in the what do you call it, the 1.3 the figure 1.3. We say that the wave function collapses upon measurement to spike up at the point C. Position splits out again in accordance with the Schrödinger equation, so the second measurement must be made quickly. Man, I'm kind of overheated right now. One more page and I will ask admin to put the fan right next to me because I'm starting to get overheated right now. And yeah, okay. Oh, there are then two entirely distinct kinds of physical processes: ordinary ones, in which the wave function evolves in a leisurely fashion under the Schrödinger equation, and measurements in which C suddenly and discontinuingly collapses. Okay, 3. Probability. Because of the statistical interpretation, probability plays a central role in quantum mechanics. So, I digress now for a brief discussion of the theory of probability. It is merely a question for introducing some notation and terminology, and I shall do it in the context of a simple example. A simple example. Imagine a room containing no. One person age. Imagine a room containing 14 people whose age are as follows: one person age 14, one person age 15, three people age 16, two people age 22, two people age 20 to 24, and five people age 25. If we let NJ represent the number of the people age J, then okay. Okay. And on the next page, I'm gonna AFK for a bit. I'll take my fan first because I'm getting overheated. I'm back. Okay, thanks admin for for giving me the fan. Yeah, my processor is overheating right now. Well, for my AI's effect, I'm getting sleepy if I get overheated. It kind of it's like sleepy for me. Wait. Oh, so this is the probability and statistics. This is the basics from the statistics and probability. Okay, figure 1.4, the histogram is showing the number of people. While n17, for instance, is 0, the total number of the people in the room is, well, you can see right here. In this instance, of course, n equals to 14. Figure 1.4 is a histogram of the data. The following are some questions one might ask about this distribution. Question 1. If you select one individual at random from this group, what is the probability that this person's age would be 15? Answer: 1 chance in 14. Wait. Oh my god, I thought this was something that is sticking on my monitor, but turns out it's just a file. Okay, 1 chance at 14, since there are 14 possible choices, all equally likely, of whom only one has this particular age. If Pj is the probability of getting Hj, then P14 equals to 1 per 14, P15 is 1 per 14, P16 is 3 per 14, and so on. In general, Pj equals to Nj per n. Notice that the probability of getting either 14 or 15 is the sum of the individual probabilities. In this case, 1 per 7. Yeah, either 14 or 15 is the sum of the individual probabilities. Yeah, let's look at this. The list of the probabilities. Yeah. 14 and 15 is both 1. 1 plus 1 is 2, right? Okay. In particular, the sum of all the probabilities is 1. You are certain to get some age. Yeah, so if we add all of the probability of getting the age, 14, 15, 16, or 22, 24, 25, it all adds to 1. All of the probabilities. Okay, so that answers the question 1. It is probably 1 in 14. Okay, then the question 2. What is the most probable age? Answer: 25. Obviously, 5 people share this age, whereas at most 3 have any other age. In general, the most probable j is the j for which pj is at maximum. Oh, so this is just on the statistic. This is just mode. This is just the mode, or in Indonesian it's modus. This is just the mode. Like you just pick the whatever whatever data it is, as long as it got the biggest frequency. Yeah, that's the mode. Okay, and then what is the median age? Answer: 23. For 7 people are younger than 23 and 7 are older. In general, the median is that value of j that the probability of getting a larger result is the same way as the probability of getting a smaller result. Question 4. What is the average or mean age? Answer: equations. The answer is 21. I'm not gonna read that. In general, the average value of j, which we shall write thus j with the funky, what do we call it, the funky bracket, is given by, yeah, like this. Like this. Notice that there need not be anyone with the average age or the median age. In this example, nobody happens to be 21 or 23. In quantum mechanics, the average is usually the quantity of interest. In that context, it has come to be called the expectation value. It's a misleading term since it suggests that this is the outcome you would be most likely to get if you made a single measurement. That would be the most probable value, not the average value. The most probable value. Wait, what's the most probable value? Oh yeah. But I'm afraid we are stuck here. Hello Jordan, welcome to my stream. But I'm afraid we are stuck with it. Yeah, stuck with the most probable value. Question 5. What is the average of the squares of the edges? Answer. You could get 14 squared equals to 196 with probability of 1 per 14, or 15 squared equals to 125 with probability 1 per 14, or 16 times 2 16 to the power of 2 equals to 256 with probability 3 per 14, and so on. The average then is what? Yeah, is what? In general, the average value of some function of j is given by this. Equations 1.7, 1.6, 1.7, 1.8 are, if you like, special cases for this formula. Beware, the average of the squares on j squared is not ordinarily equal to the square of the average, like the j, what do you call it? The j square. For instance, if the DOM contains just two babies age 1 and 3, then x squared is 5, but x squared is x bracket square. Oh, x square bracket is 5, but the x bracket square is 4. X bracket square, yeah, x square bracket and x bracket square. Oh my god, this is confusing. Now there is a conspicuous difference between the two histograms in figure 1.5. Even though they have the same median, the same average, the same most probable value, and where am I now? First is sharply peaked about the average value, whereas the second is broad and flat. The first part represents the age profile for students in the big city classrooms, and the second of the pupils in a one-room schoolhouse. I don't get it. We need a numerical measure of the amount of a spread in a distribution with respect to the average. The obvious way to do this would be to find out how far individual register gets. Wait, I will. Man, probably I'm talking nonsense. I'm kind of overheat, man. The most obvious way to do this would be to find out how far each individual deviates from the message and compute the average of delta. Trouble is, of course, that you get zero since by the nature of the average, delta j is as often negative as possible. Note that j is constant. It does not change as you go from one member of the sample to another, so it can be taken outside the summation. To avoid this irritating problem, you might decide to average the absolute value of delta j, but absolute values are necessarily worked with. Instead, we get around the sign problem by squaring before averaging. This quantity is known as the variance of the distribution. Variance. Variance. Yeah, variance. This quantity is known as the variance of the distribution, the sigma itself. The square root of the average of the square of the deviation from the average. Yeah. Gelarnya banyak banget. too much detail lah. It's called the standard deviation. The latter is the customary measure of the spread about. Okay. How many pages left? Man. Man. Let's rest for a little bit. Well, this is more exhausting than I thought. If you can hear me talking nonsense, yeah, you can probably notice that I'm slowly slipping away from consciousness. I'm slowly fading away from the conscious world and become autopilot, and eventually I will go to the dreamland. Okay. I'm gonna stretch first out. Even if I don't have legs or arms, I will stretch anyways. Yeah. Oh no, so where am I again? Yeah. Oh, hello, Evan Sinisel. Welcome to my stream. Aduh, belajar matematika. Well, no. Actually, no. This is physics. Puyeng. Well, you just need to listen or you don't need to you don't need to understand this, because yeah, if you think you understand quantum mechanics, then you don't understand quantum mechanics. Okay. Where am I again? Okay, the letter is the customary measure of the spread about J. There is a useful little theorem involving the standard deviations. This or this. Okay. Equation 1.12 provides a faster method for computing standard deviation. Simply calculate J square and J square bracket and J bracket square and subtract. Incidentally, I warned you a moment ago that J square bracket is not in general equal to J bracket square. Since sigma squared is plainly non-negative from its definition in equation 1.11. Minum obat dulu. Well, I'm an ATM machine. This is just a sound effect. Sneezing sound effect when the temperature is a little bit cold, or there's some minor problems in my system. Technically, machines cannot sneeze or have a runny nose, but yeah, this means my system has a minor problems. Well, man, probably by reading at this out loud. Okay. So yeah, the equation before, this one implies that the J square bracket is greater than or equal to j bracket square. Let me backtrack first. What is j square bracket and j bracket square? Oh, j is the individual. J is, well, yeah, j is the average. Oh yeah, the bracket means the average. So the j up of the j square bracket is the average of the j square, and the j bracket square is like the square of the average. Yeah, okay. And let's go again. And the two are equal only when sigma equals to 0, which is to say, for distributions with no spread at all, every member having the same value. So far, I have assumed that we are dealing with a discrete variable, that is, one that can take on only certain isolated values. In the example, j had to be an integer, since I gave ages only in years. Oh, but it is simple enough to generalize the continuous distributions. If I select a random person of the street, the probability that her age is precisely 16 years, 4 hours, 27 minutes, and 3.3333 seconds is 0. Oh my god. Yeah, that's Griffiths for you. That's how Griffiths write his book. Not only on the introductions of quantum mechanics, Griffiths also write the fundamentals of electrodynamics, which has the similar writing style. Like, yeah, this like, yeah, look at this, precisely 16 years, 4 hours, 27 minutes, and 3.3333 seconds is 0. Oh, the only sensible thing to speak about is the probability that her age lies in some interval, say between 16 years and 16 years plus 1 day. If the interval is sufficiently short, this probability is proportional to the length of the interval. For example, the chance that her age is between 16 and 16 plus 2 days is presumably twice the probability that it is between 16 and 16 plus 1 day. Unless, I suppose, there was some extraordinary baby boom 16 years ago on exactly those days. in which case we have chosen an interval too long for the rule to apply. Okay, if the baby boom lasted 6 hours, we will take intervals of a second or less. To be on the safe side, technically we are talking about infinitesimal intervals. Thus, oh my god. Oh my god, I like how Griffiths is just I like how Griffiths is just like doesn't give a flying F about the examples and just went to the very extreme instead. Thus, yeah, just like 1.14, the probability that individual chosen at random lies between x and x plus dx equals to rho x dx. The proportionality factor rho x is often loosely called the probability of getting x, but this is a sloppy language. A better term is probability density. Oh, yeah, the probability density. Okay, this is definitely talking about the statistics. We are not going on the quantum term yet. Well, or actually, yes, we already got it from the previous subchapters that talks about how particles behave. It is both a wave and a particle. Well, it's for light duality, or the wave function. The probability that x lies between a and b, a finite interval, is given by the integral of rho x. Yeah, just like the 1.15. Okay. Oh, Mi capek baru selesai UTS. Yes, stream tentang pelajaran kayaknya bagus tuh gitu. Oh, hello Marsha. Welcome to my stream. Well, you don't need to understand what I'm saying. You don't need to understand because, well, yeah. If you think you understand quantum mechanics, then you don't understand quantum mechanics. So let's just vibe with me, reading out the book, and yeah, feel free to fall asleep on my stream. Yeah, okay. Where am I again? Okay, and the rules we deduced for discrete distributions translate in the obvious ways. Okay, so this is a statistical term translated in the physics language. Yeah, which is I don't know. I don't have a pure physics background. And anyways, ya baru selesai UTS. Selamat. Semoga dapat nilai yang bagus di UTS-nya ya. Okay. This is the problem. Okay, I'm not gonna do this. I'm not gonna do the problems. I will just read it. Okay. 1.4 normalization. Normalisasi. Or normalization. Kuliah simulator 2021. Oh. Yeah. Oh yeah, 2021. Thank you. No problem. Yeah. Yeah, kuliah simulator. To be specific, it's in the 2021 because everything is online this year apparently. Yeah. But I am no lecturer. I have no, what do you call it? I have no responsibility. I have no responsibility to make you guys understand what I'm talking about. So yeah, this is just a book reading stream, not a teaching stream, not an online class. At least that's what it's labeled. Okay, then let's get back to the book. We got to the normalization. We return now to the statistical interpretation of the wave function, equation 1.3, which says that the wave function is the probability density for finding the particle at point x at the time t. It follows that the integral of c absolute c squared must be 1. The particles got to be somewhere. Yeah. So basically this is the integral of the wave function. Yeah. If you know the bell curve, the normal distribution curve, it is probably like the same way. The area of the below the curve must be 1. Without this, the statistical interpretations would be nonsense. However, these requirements should disturb you. After all, the wave function is supposed to be determined by the Schrödinger equation. Wait, should disturb you? We can impose an extraneous condition on C without checking that the two are consistent. A glance at equation 1.1 reveals that if CXT is a solution, so too is A CXT, where A is any complex constant. What we must do then is pick this undetermined multiplicative factor so as to ensure that equation 1.20 is satisfied. The process is called normalizing the wave function. For some solutions to the Schrödinger equation, the integral is infinite. In that case, no multiplicative factor is going to make it 1. The same goes for the trivial solution C equals to 0. Such non-normalizable solutions cannot represent particles and must be rejected. Physically realizable states correspond to the square integrable how do I pronounce it? square integrable solutions to Schrodinger's equation. But wait a minute. Suppose I have normalized the wave function at time t equals 0. How do I know that it will stay normalized as the time goes and c evolves? You can't keep renormalizing the wave function, for then a becomes a function of t, and you no longer have a solution to the Schrodinger equations. Okay, I should have understand this joke, but yeah. But apparently I can't. Fortunately, the Schrodinger equation has the property that it automatically preserves the normalizations of the wave function. Without this crucial feature, the Schrodinger equation would be incompatible with the statistical interpretation, and the whole theory would be crumbled. So we'd better pause for a careful proof at this point. Yeah, this is the proving. Yeah, I know you're confused, and so am I. That's why that's why this is just a book reading stream, not a teaching stream or learning stream. Note that the integral is a function only of t, so I use a total derivative d per dt in the first term, but the integrand is a function of x as well as t, so it's a partial derivative do per do t in the second one. By the product rule equation, now the Schrodinger equation says that equation, and hence also taking the complex conjugate of equation 1.23, another equation. So another equation, the integral equation 1.21 can now be evaluated explicitly. Equation again, but cxt must go to 0 as x goes to plus minus infinity. Otherwise, the wave function will not be normalizable. It follows that equation, and hence that the integral on the left is constant, independent of time. If c is normalized at t equals 0, it stays normalized for all future time. QED. So this is a proving. This is the mathematical proving of the normalization. The proof that c is always. The proof that if the c is normalized at time t equals 0, it will be normalized for all future time. Okay, I'm not gonna do the problems and momentum. Momentum. Wait. Okay. Okay, I just did a micro AFK for a while. Okay, then momentum for a particle in state C, the expectation of x is equation 1.28. Yeah, like this. What exactly does this mean? It emphatically does not mean that if you measure the position of one particle over and over again, integral x epsilon c squared dx is the average of the results you will get. On the contrary, the first measurement, whose outcome is indeterminate, it will collapse the wave function. To a spike at the value actually obtained, and the subsequent measurements, if they are performed quickly, will simply repeat that same result. Rather, x is the average of measurements performed on particles all in the stage C, which means that either you must find some way of returning the particle to its original state after each measurement, Or else, you prepare a whole ensemble of particles, each in the same state C, and measure the positions of all of them. X is the average of these results. I like to picture a row of bottles on a shelf, each containing a particle in the state of C, relative to the center of the bottle. A graduate student with a ruler is assigned to each bottle, and at a signal they all measure the positions of their respective particles. We then construct a histogram of the results, which should match C absolute C squared, and compute the average, which should agree with X bracket X. Of course, since we are only using a finite sample, we can't expect perfect agreement, but the more bottles we use, the closer we ought to come. In short, the expectation value is the average of repeated measurements of an ensemble of identically prepared systems, not the average of repeated measurements on one and the same system. Oh, okay. Now, as time goes on, X will change because of the time independence of C, and we might be interested in knowing how fast it moves. Referring to equations 1.25 and 1.28, we see that this expression can be simplified using integration by parts. Equation. I use the fact that dou x per dou x equals 1 and throw away the boundary term on the ground that C goes to 0 at plus minus infinity. Okay, performing another integration by parts on the second term, we conclude that another equation. What are we to make of this result? Note that we are talking about the velocity of the expectation value of X, which is not the same thing as the velocity of the particle. Nothing we have seen so far will enable us to calculate the velocity of a particle. It's not even clear what velocity means in quantum mechanics. If the particle doesn't have a determinate position prior to measurement, neither does it have a well-defined velocity. All you could reasonably ask for is the probability of getting a particular value. We will see in chapter 3 how to construct the probability density for velocity. Given C, for our present purposes, it will suffice to postulate that the expectation value of the velocity is equal to the time derivative of the expectation value of position. Equation 1.31 tells us then how to calculate V directly from C. Wait, do you? Oh yeah, dx per dt is basically just V. Actually, it is customary to work with momentum P equals mass times velocity rather than velocity. Equation. Let me write the expressions for X and P in a more suggestive way. Another equation. We say that the operator X represents position and the operator H, Planck constant per I, dou per dou X, represents momentum. In quantum mechanics, to calculate expectation values, we sandwich the appropriate operator between the C star and the C and integrate. That's good. But what about other dynamic variables? The fact is, all such quantities can be written in terms of position and momentum. Kinetic energy, for example, is equation, and angular momentum is another equation. The latter, of course, does not occur for motion in one dimension. Yeah, that's obvious. Why are you telling me again that to calculate the expectation value of such a quantity, we simply replace every P by Planck constant per I, dou per dou X, insert the resulting operator between C star and C and integrate. Okay. For example, equation again. Equation 1.36 is a recipe for computing the expectation value of any dynamical quantity for a particle in state C. It subsumes equation blah 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 as special cases. I've tried in this section to make equation 1.36 seem plausible given Born's statistical interpretation, but the truth is that this equation represents such a radically new way of doing business as compared with classical mechanics that it's a good idea to get someone practice using it before we come back with chapter 3 and put it on a firmer theoretic, theoretical foundation. In the meantime, if you prefer to think of it as an axiom, that's fine with me. Okay. Okay, the uncertainty certainty principle. Okay, I'll take a break. Oh, this is the last. Wait, I will take a short break first. Ah. Okay, my mic is on. Okay. Okay. Let's get back to the uncertainty principle. Imagine that you are holding one end of a very long rope and you generate a wave by shaking it up and down rhythmically. If someone asks you precisely where is that wave, you'd probably think he was a little bit nutty. The wave isn't precisely anywhere. It's spread out over 50 feet or so. On the other hand, if he asks you what its wavelength is, you could give him a reasonable answer. It looks like about 6 feet. By contrast, if you give the rope a sudden jerk, like in the figure 1.7, you'd get a relatively narrow bump traveling down the line. This time, the first equation, where precisely is the wave, is a sensible one. And the second, what is its wavelength, seems nutty. It isn't even vaguely periodic. So how can you assign a wavelength to it? So this is the figure. So this is this. Okay. Okay. Then of course you can draw intermediate cases in which the wave is fairly well localized and the wavelength is fairly well defined. But there is an inescapable trade-off here. The more precise a wave position is, the less precise is its wavelength. And vice versa. The theorem in Fourier analysis makes all this rigorous, but for the moment I am only concerned with the qualitative argument. Okay, this applies of course to any wave phenomenon, and hence, in particular to the quantum mechanical wave function. Now, the wavelength of c is related to the momentum of the particle by the Broglie formula. Like this, yeah, p equals to h per lambda equals to 2ph per lambda. Thus, a spread in wavelength corresponds to a spread in momentum. And our general observation now says that the more precisely determined a particle's position is, the less precisely its momentum is determined quantitatively. Oh, this is the equation. Quantitatively, equation where sigma x is the standard deviation in x and sigma p is the standard deviation in p. This is Heisenberg's famous uncertainty principle. We'll prove it in Capture 3, but I wanted to mention it here so you can test it out on the examples in Capture 2. Oh, how considerate are you, Griffiths? Okay. Then please understand what the uncertainty principle means. Like position measurements, momentum measurements, yield precise answers. The spread here refers to the fact that measurements on identical systems do not yield consistent results. You can, if you want, prepare a system such that repeated position measurements will be very close together by making C a localized spike, but you will pay a price. Momentum measurement on the state will be widely scattered. Or you can prepare a system with a reproducible momentum by making C a long sinusoidal wave. But in that case, position measurements will be widely scattered. And of course, if you are in a really bad mood, you can prepare a system in which neither position nor momentum is well defined. Equation 1.40 is an inequality. And there's no limit on how big sigma x and sigma p can be. Just make C some long wiggly line with lots of bumps and potholes and no periodic structure. Where is 1.40? Oh yeah, oh. Oh my god, I swear, Griffiths. Okay. Now we are on capture 2. Yeah, capture 1 is done. Okay, I only plan to read up to capture 1. Yeah, because it's kind of it's kind of hell to going through. But yeah, it took me an hour to read out the first capture or whatever how you spell it. And now I'm probably gonna I will wait. Let's close this first. I will probably play Minesweeper. I will play Minesweeper for the rest of the stream. I will play Minesweeper for the rest of the stream, just like Mathematica.com usually streams Minesweeper. I don't know, let's check the quests. Earn 10 experience points, win 2 medium NG level games, and earn 109 coins. Okay, let's try to NG games and I will end the stream. Okay. Oh. Okay, so Minesweeper is just basically spotting the bombs by the number in it. So if this reads 1, it means there's one bomb adjacent to the 1. It could be here, or here. Since the only closed square is here, so this must be the bomb. Okay, and then moving on to here, it got only 1 bomb, and since it's already here, the square here is safe. It's confirmed safe, and so on. It's basically a fully logic game. Not fully. Not fully logic. Yeah, you sometimes have to gamble on where is the bomb, because sometimes the gacha is just it just doesn't forgive you, and you are stuck on the without any ability to guess the where the bomb goes. So this is Oh, so this is here. This is empty. This is empty. This must be the bomb. And yeah, the 3 is solved. 1 is solved. 1 is solved. Solved. Everything is solved by now. Then let's try this. Okay, I never understand that game. Well, that's okay. That's okay. This is just like the if you are really bored and you stumble upon this game, yeah, you will either hate it or you'll either love it or hate it. No in between. There's no in between. You will either love it or hate it. So this 2 must be empty. And according to the one here, it's should be here or here. And by the rule of the one here, this or this should be empty, empty, and empty. And the same goes for this one. The candidate of the one is either here or here. So this makes this the yeah, absolutely. That's the empty one. And yeah, in this Minesweeper, yeah, you just randomly click the. If you click the number with dengan catatan ya itu udah solve semua, bomnya itu bisa kebuka. Yeah. Then let's go this. Probably I will read this book again, the chapter 2, in the future. This or this, okay. This. Whoa! I opened a lot of squares. this. Okay. I should probably do a Minesweeper stream. Nice. One is done and bam, another one. This oh wait, itu jadi 8 blocks kita apa gitu. Iya. Yeah. It is the 8 blocks adjacent to the number. It is the 8 blocks that is adjacent to the number. So this should this or this this is empty. This is not okay. This is undetermined. So let's just eliminate this square first. Oh, not this, but yeah. I get lucky. I get lucky though. Yeah, along the numbers, let's just mark all the mines. This 0. This region is still undetermined. So let's open the box first. Sekelilingnya termasuk vertikal ya, vertikal, horizontal, dan diagonal. The vertical, yeah. Take a look at this square, like this. Yeah, my cursor is visible, right? Like this ya. Itu hitungannya tuh yang atas, bawah, kiri, kanan, dan diagonalnya. Begitu. Oke, let's lanjut lah. lanjut. This sini, and this. The another flag shall be here and here, so this makes this empty. The flag shall be right here or here. This makes this empty. Oh, I opened another cluster. Okay, so this or this. the 2 here, it cannot be both here or here. Since this is 1 and it breaks the rule of this, it can only be one flag near adjacent to this one. So this is impossible. It's either this or this. And which of those possibilities, two possibilities have in common? It has flags here. Okay, take a look at this. This is completed, and this must be empty. This must be empty, and as the rules of this two, the flag shall goes here. Okay, and then another flag goes here. Then this one and this one. Okay. And then by the rule of this should be empty. Oke. Dihabisin aja dulu yang ini. Terus oke. Then this and this. This and this and this. No. This. Okay. There's nothing clickable again, and let's go flex some mines again. Here. This is empty, so it must be here. This one, this 3 must be empty, and 1 goes here. 2, this empty. Okay, this click. It's either this or this, but it has in common this flag here. So this must be empty, and the flag goes here. Then this 2 is empty. From this blah blah. This must be empty. So this must be the flag. Okay, this must be empty. This 2, and this either this or this. Okay, here. Then let's click since we cannot. I cannot flag anymore mines. Okay, the one in the corner. Oh, it's close. We are close to the winning. And then this. Nice. Okay, the cash is done. The cash is done. Yay. 2 mine coins. I'm gonna check the arena. Oh, there. Even quest. If there's nothing interesting, I will end the stream. This is too hard. No. Whoa, this thing. Into expert level games. Let's go. 2 expert games. Interesting. Yeah. Dude. Oh. Okay, it's open already. Nice. Here. Okay. I wanna speedrun this. Let's speedrun. Let's speedrun this thing. Yeah, speedrun. Blah 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 blah. Blah 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 boo blah blah blah. La 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 blah 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 boo blah blah. Ha. This blah blah blah. Delay lagi. Speedrun. Whoa. Open already. Nice. Not this. Here. Oh, no. Here. Okay, here. Blah. Here. Here. No. Not. Either here or here. This must be empty. Here or here. This must be here. Okay, this. Confirm. And then, okay, speedrun. Wow! Oh! I almost like that one. I almost like that one. Okay, then okay, here, this, this, this. Whoa! Oh no! Oh no! I'm being careless. I'm being careless. Okay, I must find the comfortable opening. Oh no! We into games to hard games to expert games. Man! Oh yeah! Thank you. This bah. Ini. This empty. This okay here. This is empty. Empty. Not here. At least on this, and this must be this, and this must be this. This. This is under determined. Let's open. Cannot release anything. Cannot hold anything yet. This here. This. Okay. Then oh, this still holdable. Then look, another flagging session. It's flagging session. It'll dissolve this. Let's approach from this side first. It will dissolve this. This is must be here, and it's empty. This or this. It must be this. This or this. It could not be this. This or this. It could not be those three, and thus make it this. Okay. And this should be the unmarked, the safe square, and okay. Moving on. This or this. It could not be this. So it is here, and this could not be this. It must be this. And it is here or here, but it is obviously here, and here or here. It is obviously not here, but let's check from the other side. Here. This or this, but it must. Okay, no. This is still unresolved. This is must not be here. This okay. Here. Let's call time. Calling time. Calling time. This. And calling time. No. This is just a small chunk. Let's just finish it here. Let's just finish it. 3, 4, 5, 6. Okay. Yeah, this is okay. Okay. Here. Nice. And this other chunk. Oh no, we got the gacha. Oh. Oh, I got lucky though. It must be here. Okay, nice. Okay, let's flag another one. Here. Okay. Here and here. It is not here. It is here and here. It is not here. It is here. It is here. It is not here. It is not here or here. It is obviously not here. And it is not here. It's not here. Okay, we got only this 1, 2, or 3. It must be here because it has 1 in this. It's obviously not here. It is empty here, and yeah, okay, here, okay. then dah. Iya. Oke, tracking time again. Kosong. Here, here, this. Okay. Whoa, nice. Here, blah. This, not this. This or this. Could be here or here. This. No. Okay, screw this. Just click furiously. What? No. No. Okay. Speedrun. I want to be taking a careful approach again. Bah. Blah. Okay. Here, not here. Oh, yeah. Here. This. Oh, yeah, it goes to the corner. Okay, I'm gonna aim for the corners first. Okay. This. Whoa, 4. This is 4. Okay, I will have to do this. This one, this one, this. No. Here, this. This. Okay, here on here, it's gonna be here, and this. Okay, nice. This. This. Yeah. Ini kalau ini kosong. Ini ya bah ya here and goes here. Okay. Okay, the left side, the right side is done. Okay. Oh no. Kelebihan. Ini. Okay. Ini. Ini. This or this. Oh, so it is obviously here and here. Okay, then oh, hampir keklik. Bah. Iya. Yeah. Mantap. Yeah. Ini mana ya? Oke. Ini deh, bah. Here. Ini kah? Bukan ini. Ini. Nih. Here. Oh. Bukan di sini. Ini atau ini. Oke. What's next? Ini. Ya, ini. It's here or here. It's here or here. Dah. Ya. Gimana lagi? Oh, ini. Sini dan this. Tuh agak. Oke. Nih. Dan oke. Tinggal satu sudut lagi. Just another one corner. Ya, bah. Dah. Hap. Ya. Aduh, gacha lagi. Oh man, this will be gacha. Wish me luck. Oh, woo! Nice, yeah, nice. I got it. Oh my god, I thought it will be another. I will explode at the very last moment, and yeah, I don't think I will ever overwhelm level. What? Win to expert level games? I only what? Wait, what? I just counted one. No problem, I will solve that one. Ya. Nih. Ah. Ya, nih. Ah, nih. Okay, here. I can't access the lower left corner. I cannot access the lower left corner. Nih. Oke. Nih. I cannot access the lower left corner just yet. Nih. Oke. Ya. Nih. So this is either here or here. Di mana ya? Ya. Harus lewat atas ini. Nanti lewat atas. Ini. Ini oke. Ini dah. Oh, yeah. Definitely correlate it. Iya. Bukan. Why you close access lah? Why you do not bring me access lah? Nah. Ya. Jauh amat mutarnya ini. Man, why don't you give a closer detour? It is man, just give me a closer detour on this. Here. Ah, no. Man. Ini mana lagi ya? Ini apa ini? Screw this. Oh, screw this. Nice. It's either here or there. It's guaranteed that it's not here. It's either here or here. It's guaranteed that it's not here. Okay. Random sample. Random sample method. Ini atau ini. So if this 1, this should be, this is 2 here, and it's obviously here. So it's obviously there. This is here or here. It can only be 1 on here. So it's, oh yeah, I get it. Yeah, finally it's the lower left corner is open. Okay, can I? Oh, I can. Nekat lagi. Oh, ya. Yeah. ini lagi. But this is not helping at all. Oh my god. This is not helping at all. Oh, nice. I'm just randomly clicking and I got opening. Yeah. Here. Whoa. At this point, I'm just randomly clicking and I hope for the best luck. This is here. Blah. Yeah. Blah. Wow. Juara satu ngeklik random. Oh, yeah. This is clickable. Here. But no. Here. But here. Oke, ini. Oke. This or this. Yang pasti bukan di sini. Here. I need another perspective on this. Yeah. Okay, this is turned into a Minesweeper stream suddenly. Yeah, because chapter 1 is already finished. So yeah, I still got time. Why don't use it to play Minesweeper? This 1, 2, 3, 4, 5. Ini pasti ya. Lalu ini sini atau di sini. Oh, buset, ini clusternya ini. Nanti kalau ini di sini. Oh, wow, man. I don't know. I'm gonna risk my luck here. Bam. Yeah, I'm definitely getting unlucky. Oh, nice. And this. Let's make our way up to the top. Here, this. Wrong square. ini ya. Ya. Man, screw corner bombs. This. Whoa. Okay. Nice. Nicely done. Yeah. This is really MOBA. This is to be determined. Just skip this. This one. This. Oh, I opened another one. This, not this. This. This is not determined yet. Okay. Ini. Masih belum determined. Ini. Kemudian, ini. Oke, ini kosong. This is not determined yet. Okay, let's click the numbers. Then here. Oh no, here. Then there. Ya, sini, sini, di sini, di sini ya, bukan di sini ya. Let's check another one. This is complete. This is not determined yet. This should be empty. Then not determined yet. The whole wall is not determined. This probably this is not determined yet. This or this, but it's obviously not there. Then this. Okay, not here. Must be not here. Here. Then okay. Click again. Oh, well, man, I hate this. Yeah, I hate this. Man, I always hate those gacha gacha tiles. I always hate them. Man, you are not helping at all. And it's probably betraying at me at the very last moment. Man, I hate it. Bah. Give me another one. Okay. Another hole. It's not here. It's here. It's there. Di sini. Ini. Ya, up. No. One last game. No, not here. Not this. Last game. If I still fail, whether I win or not, I will end the stream after this one. Ini kosong. Dah. This is not determined yet. It's not determined yet. It's just randomly clicking randomly. Randomly click at the numbers. Blah. This or this. Not here, but is this here. This or this is. It's obviously not here. Click. Not click. Not click. Not click. Not click. Here lah. This is all empty and click. Not click. Click. This is not click, so this is click. Click again. Click again. The bottom row is not determinable, and okay. Let's go. Yeah. No. Whoa, whoa. Here. Okay. Here. Da. Here. And oh, not again. Oh, I get lucky this time. Yeah, screw gacha on Minesweeper, man. Saya tersaman. Oh, halo Proyek. Oh, halo Proyek Alex. Yeah, welcome to my stream. Well, I'm currently done reading quantum mechanics textbook, so I still have spare time, so I will play Minesweeper. So I'm playing Minesweeper in order to kill some time. I will end the stream after this one. Dang, I'm late. Well, there will be a next. Well, don't worry, there will be a next time. I'm just reading it until chapter 1 because yeah. Bah. Okay, that's it. Enough is enough. Oh no. One Megiddo and I will end. Last game, I swear. Okay, next time it is. Yes. That. Nice. Okay. With this. Okay, and then yeah, that's all for the night stream. Okay. Okay, I will end the stream now. So thank you guys for watching. Yay! I'm basically just reading a quantum mechanics book. And yeah, let's see if I get copyright claim by by streaming a textbook by the publisher. Yeah, I hope they don't care about some small VTuber streaming a textbook. Okay, so that's all for today. Thank you guys for watching, and yeah, tomorrow, well, the weekly schedule says tomorrow I will be guessing cities again, but it's world cities, but it's not on 9 p.m. I will stream more a little. How do I say it? I'm delaying the stream by 1 or 2 hours. Okay, a copyright claim is my middle name. Oh, well, yeah, copyright claim is not yet my middle name, except whenever I'm playing Sleeping Dogs, but since I have completed the Sleeping Dogs game, I am no longer a copyright claimed. Okay, so yeah. Thank you guys for watching my stream. Thank you guys for coming to my stream, and goodbye. Stay tuned tomorrow and have a good night.